Quando iniciar, você pode.
Já tá no ar.
Boa tarde a todos. Boa tarde. Vamos iniciar, certo? Boa tarde a todos. Boa tarde aos presentes. Boa tarde aos que nos assistem, que estão nos acompanhando pelo YouTube. Meu nome é Andressa, eu sou professora no Departamento de Estatística da UFRN. E essa palestra faz parte do ciclo de seminários do Departamento de Estatística da UFRN. No seminário de hoje, nós teremos o professor palestrante convidado, o Geoff, presente, né? Ele é professor na Universidade da Virginia Tech. Tenho aqui algumas informações sobre o professor. Ele já esteve aqui em 2017 para um workshop em planejamento de experimentos de processo estatístico de controle e está aqui novamente, né, na UFRN, no Departamento de Estatística, como professor visitante. Ele vai passar um período aqui, né, durante o mês de maio, esse finalzinho do mês de maio, e no mês de junho, julho e agosto. Então, ele está aqui, a vinda dele é financiada pela Fulbright, e o propósito da visita dele é fortalecer as áreas de engenharia estatística e estatística industrial. Ele está aqui, né, na UFRN como professor visitante do PPG+, e também do programa de pós-graduação em engenharia de produção. So, thank you so much for being here. I would like to thank you for your availability to this talk and to say that we are very glad to welcome you to our department.
Thank you. Obrigado. My only word. It is a pleasure to be here. So, we're doing this in English.
Okay.
Everybody's okay? Yes. Okay. If I go too fast, let me know. Okay? So it really is an honor and a privilege to be here. I think there's a reason for this. Carla and Andre and several others from Brazil asked me at an English conference several years ago to apply for a Fulbright. And they forgot to tell me that the deadline was less than 3 weeks away. And we were successful, which means there was a definite need in Brazil for what we had proposed. And I'm very humbled and honored by that. It was postponed 2 years for COVID, but I'm so happy that we could come. It's a little strange, and my schedule is a little broken, but the plan is I will do a total of 2 months this year and come back next year to finish my full month, which will be another 2 months, another 9 months. So I'm very much looking forward to this project. I'm looking forward to starting something here with all of you, especially with Carla and Andre. But I want to see it grow and prosper. And that's the idea. It's the reason why the Fulbright program was excited to present us with this award. And it's to us, it's not just me, it's to the whole group. So, with that, I'd like to talk about, I hear the echo. With that, I'd like to go ahead and start my talk. I'm going to talk about statistical engineering. I want to talk about some of the work that I am currently doing. I have one project where I will show you real data, and I can't tell you anything about those data. Absolutely nothing. En español, nada. Okay? But you'll have a hint what the project is, and it's high profile. Okay? But I want to illustrate that the thought of Walter Shewhart from the 1920s, published in 1931, should be revolutionizing the whole field of statistical process monitoring, given Industry 4.0. His thought was that radical, and they don't understand it. But now we have the data to illustrate what he was really talking about. I find that thrilling and fascinating. And we're dealing with really cool problems, and we have to use these kind of tools. So far, so good? Okay.
Yes.
Am I speaking too fast? If I get excited, I will throw something at me. That's what my wife does.
Yes, here.
That's good. I might catch that. So can we start this high? So the title of this is Shewhart, Statistical Engineering, which is a new discipline. It's evolving. Our project is all about statistical engineering. I want you to have a clue what it is. The course that we're teaching focuses on statistical engineering. And talk about that in the context of Industry 4.0. So far, so good? Okay, next slide, please. Outline, I want to talk about the changing landscape of Industry 4.0. And it's very different. So what I was taught in the 1980s in graduate school, very good foundation. It has helped me throughout my whole career. But I had certain benefits other students didn't have. I had a very broad education. I actually have a degree in philosophy. I was just short of a chemical engineering degree, and I have an MS and PhD in statistics. I can think of both sides of the mind. And I want us to appreciate that. So I want us to understand the changing landscape, the role of statistical engineering. I'll introduce the concept. I'm going to talk quite a bit about Shewhart. And I'm going back to the original Shewhart, and I'm going to try to help you understand it. First, from an example that he could relate to directly. But more importantly, in the context of a very, very real and important problem. So far, so good? And everything you've taught about common cause variability, if you had any of that, I'm not putting any blame on any of the professors. It's all wrong. Because he doesn't understand how Shewhart was really approaching it. And it's fascinating. Because if you're going to implement proper statistical process monitoring and control in Industry 4.0, we need to go back to this thought. And it's wonderful to go into that. So far, so good? So this is not to cast, any kind of blame on people. This has been, it has evolved over time. It's how I learned statistical process monitoring, statistical process control. So understand this is an evolution for me. So I want us to deal with the new reality and then talk about the challenge. If I reference Shewhart, it's from his 1931 book, but the original work is 1924. So far, so good? Many of you have been taught that a control chart is a series of hypothesis tests, right? Oh, it's not true, but that's what we're all taught. That's what I have taught. I'm guilty. Understand? Maven Pearson lemma, which is the foundation for hypothesis testing, is in the 1930s. Shewhart's thought predates that by 10 years. You cannot make the claim that what Shewhart proposed was a series of z-tests. Cannot make that claim. Have I got your attention? Okay. So next slide, please. I thought I had a picture here. Oh, let's show the next one real quick. I'll come back. That's the Trent 1000 engine. Okay. Rolls-Royce, designed specifically for the Boeing 787. We got the idea here? They're losing $1 billion a year on it. None of the people who make jet turbines make money selling the turbine. They make the money on the maintenance contract. Let's go back to the slide before that. We have a context. $1 billion a year, that's 5 billion reais a year. That's got a lot of attention within the organization. Fair enough? These are the kind of problems I'm talking about. This is classic Industry 4.0. So let's go back to the previous slide. So the characteristic that is driving the Trent 1000 is called the turbine gas temperature. It's the hottest point in the engine. For those of you who have been trained in thermodynamics, engine cycles like a Carnot cycle, a Brayton cycle, all work more efficiently the higher the temperature it is. So what did they do for the Trent 1000? There was pressure from the airlines to get more fuel efficiency, a little bit longer flights. So they jacked the temperature up. They designed it purposely to operate at a higher turbine gas temperature. They did not anticipate that it had an impact on the metallurgy. We were beginning to surpass with the titanium crystal specifically. So far, so good? Okay. So, That temperature changes not like a standard statistical process control chart. It is known that temperature is going to increase over the life of the aircraft. Once it increases to a certain point, we call that degrading to a certain point, they do maintenance. There's maintenance for other issues as well. But the critical safety factor is that turbine gas temperature. So far, so good? Okay. So, we need the predictive EGT. This is not Shewhart's world, but you can adapt Shewhart to do this very beautifully. Okay? So far, so good? Those of you who had statistical process control, statistical process monitoring, you would do something called like profile monitoring on this. What they're doing won't work. No way. Because it doesn't understand the core problem. Help me, I'll try to illustrate that. Okay? So let's go ahead to the next slide. Here we go. What's the issue on the monitoring problem? For the Rolls-Royce engineers, it's called measurement uncertainty. 6 years ago, Rolls-Royce tried to get me involved in measurement uncertainty on a corporate level. Virginia Tech has a Rolls-Royce Center of Excellence, so it's supposed to be through that. People in Derby want me involved. The mechanical engineering department did not. Guess who won that conversation? The mechanical engineering department. Because they controlled that specific state. There was a change in leadership, and the first thing that the new Rolls-Royce professor in mechanical engineering did was to recruit me to get me engaged for this particular problem, but for more than that. But what they call measurement uncertainty ultimately is prediction capability for us, and we got to deal with both bias and with variance. So far, so good? We've got to understand the sources of variability. Now, in a very good experimental design course, you learn about blocking. You may learn about random effects, okay? Variance components, sources of variability. Engineers have no clue. By the way, machine learners have no clue, okay? They really don't. They're beginning to get a clue. Bayesians think they can do it with hyperpriors. That's just a mathematical exercise. Okay? What it is you got a categorical variable and you need to change the relationship based off that categorical variable. In this case, it's very, very complex. Am I making sense? Okay. Our available flight data. Now, we do not get the 1 Hertz data. That's every second of the flight that data exists. The airlines own that. That's overwhelming. And we don't need that for this project. But what we do have is a summary of the 1 Hertz data over critical flight segments for every flight of the Trent 1000, for every flight of the Trent 700 from about 2000. This is a large amount of data. So far, so good? Okay? It's a big data problem. Rolls-Royce gave this problem to a very distinguished data science institute in the United Kingdom. And let them play with it. And they came back and said, okay, Rolls-Royce, you may think this is big data, but it's not big enough, which meant they couldn't find anything. So far, so good? Why couldn't they find anything? You have to understand what are the sources of variability. They had no idea. So far, so good? Okay. Well over 100 different characteristics. Those characteristics are going to be Shewhart's common cause. They're common causes. That's a system of common causes. There's nothing random about them. We know them with extremely good accuracy. There is a deterministic relationship on their impact. There is nothing random about their contribution. Have I got your attention? Okay. Next slide. Our attempt to do this, I can explain the algorithm almost to a point. Fair enough? Okay, because we're just beginning to really explore the algorithm with the data. But the idea is peel the layers of an onion. Onions have many layers. We take the outside layer off, and we see what's left, and we try to take the next layer off. Think of that as removing the variability, because that's exactly what we're doing. So far, so good? First step, first principle models. Rolls-Royce, all the jet turbine manufacturers, all the airlines have first principle models to explain critical quality characteristics of the jet engine. They all do. It's going back to the basic thermodynamics. I thought it was more complicated than that, but it's just the basic thermo. Many of them use code, a modification of code developed by NASA, called the NPSS, and I've forgotten what it's called. The initials are, the N is NASA, but everything else I don't remember. But they all have variations of that, and they have their own thermodynamic data, and they use that for the initial prediction. And that's actually part of the data that we receive. This is called the engine health monitoring data. And they actually compare what the model says should be the temperature to the actual temperature reported for that particular flight set. So far, so good? That's an important quality characteristic, the difference between those two, because it's a measure of degradation. The first principle models assumes no degradation. There's been no deterioration. So it gives us an opportunity to explore what has changed. So far, so good? Okay. So what we do is we'll take the first principle models, and then we will predict what is remaining after we subtract the first principle models with the actual engine health monitoring data. Okay? Nice regression model. We're going to do more than that, but so far that's as far as I'm going to take you today in this talk. The ultimate goal is to learn from that to do a feedback loop into the first principle models to improve them. To incorporate formal degradation models based off the data and good basic physics. These degradation models are all differential equations. So they lead to nice, sometimes linear, but generally nonlinear models. We can incorporate that into first principle physics. Oh my God, we just got another quantum leap in improvement. You got the big picture of what we're trying to do. Welcome to Industry 4.0. Okay? Next slide. Statistical engineering. This is an example of what we're doing, a new discipline we call statistical engineering. So I want to talk about this briefly. And that's the course that we're teaching this summer. My summer, your winter. Okay? And this is my summer vacation. I'm spending it in winter, doing something I love to do. This is really kind of nice. I'm having the time of my life. Okay? My wife will be on the beach when she comes here. I'll be working with people here, and I'm still going to do some stuff with NASA and with Rolls-Royce. I'm just going to be playing. I don't have to worry about grading papers, anything like that. I'm going to be having the time of my life. Are we all good with this? All right. This is a kind of classic example of a very complex business opportunity, because losing $1 billion a year is an opportunity. If we can come up with a way to reduce that and help them build better maintenance contracts in the future, this is nothing but money for them. This is the kind of thing that makes senior leadership within the organization really, really happy. You have people who can pull this off. You have the people who have the right skills. This problem is too complex just to hand to a data science institute and expect anything but junk. This is something that requires intense collaboration between engineers who understand the basic first principles, who understand the operation of the aircraft. You've got to have, actually we have geoscience involved in this, because one of the causes of degradation is sand. And sand combined with ocean salt water does really major damage under certain circumstances to a jet turbine. We have geoscience engaged in this. Okay? We've got business people engaged with this. Ultimately, this is a business problem. Are we seeing the breadth of the disciplines that are required to do this? Okay? If necessary, we will bring the machine learners in. That's fine. They're over in computer science at Virginia Tech. And they're happy to do that. We just don't see a place for them yet. But they may be, and probably will. This is getting together the right people in a room with the right skills. It's called learning how to collaborate, but do it in a systematic manner. Some organizations have done this well for years, others have no idea how to do it. And generally, the people who have known how to do it do not pass that knowledge on to the next generation. When they retire, it's gone. Classic problem within NASA. They don't pass the knowledge on well. This is a new discipline designed to show what are the proper strategies for dealing with these problems. That's what we're teaching this summer. Okay. So collaboration, proper and insightful data analysis, and teamwork. Oh my God, if the teams can't function, this is disaster. Okay. Next slide. This is a classic example. Here are the groups that are in there, and there are very senior leaders, in fact, to just below board level, that will have impact on this project. We have to make reports on a regular basis, and every so often we have that layer just below the board. Okay? The key to this is using scientific method, because that's the core of the solution process. And what we're doing, as I said, is an Industry 4.0 version of statistical process. Are we good so far? Okay. Next slide. Shewhart was really applying scientific method. It really was, in a very rigorous way. And I'll tell you a little bit more about his background, I think, in the next slide. But what he was trying to do was a journey, and it literally is a journey if you read this. People who've done statistical process control, originally the literature was just, here, this is how you do a control chart. It's a series of z-tests. Then people got concerned, well, how do you estimate control limits? You got to have a period there. So that led to phase 1 versus phase 2. But it was always a series of z-tests. Even Hotelling's t-squared is a variant of a series of z-tests. The stuff they do for profiles is to force something unnaturally to be a z-test. Okay? Shewhart's not thinking that way. He literally is doing an active investigation over time. He would not recognize what you call phase 1. He would say that's actually the control chart. And what you call phase 2 is the result of doing phase 1 correctly. As he says, you ultimately reach the point where you don't have anything out of control. You're just doing this to make sure that if something changes, you see it. And what's driving all of this? And the journey's end, the process begins to look like it obeys statistical laws. He talks about it. It looks like it. But that's a stretch. You're making some pretty strong assumptions. Okay? But this is what he would see as why it's not very interesting, because if you've done this journey correctly, you have identified every one of the assignable causes, and if it was economic to do so, they are correct. You just got to make sure that the protocols stay in place. And for his universe in the 20s and 30s at Western Electric, very powerful tool. But the key is systematically eliminating all the causes. How do we identify a cause? It's the outlier. Shewhart is not interested in formal testing. He's interested in identifying outliers. And what does he say you do with the outlier? It's not a statistician saying, oops, we got an outlier here. You know, there's a commercial in the United States. Somebody looks like a bank guard. And he says, well, you know, I'm not a bank guard. I'm just here as a sentry. You know, I don't even have a weapon. You know, it's like, what good are you? You know, the whole point is you can sound the alarm that there's a bank robbery. We know that. But that's not helping the people who are in the bank robbery. Got the picture? He's monitoring the situation. He's not controlling it. The goal is to control it. Okay? So next slide, please. Look at his background. PhD from Berkeley. Back then, Berkeley's still a very good school, but it was a really good school then, too, in physics. Deming had a PhD. Anybody in the room know what discipline his PhD was in? Physics. in a similar time period. Okay? So, Deming must have been about 10, 15 years younger than Shewhart, best I can gauge. His first job was Western Electric. In 1924 is his first evidence of the control chart. From 25 to 56, Western Electric, he broke up into several groups. He went with Bell Labs. This is the book that is considered the first authoritative, comprehensive explanation of statistical process control. Knows its economic control of quality of manufactured product. Economic. The issue is, how can I make money? Got the idea? It's not how do I pick up a change in parameters. It's how can I make more money by improving the process. His primary engineering experience is discrete parts manufacture. He's not dealing with large-scale systems. That jet turbine is a large-scale system. Are we beginning to see some of the differences here? Okay. Next slide, please. Notice what's going on in the physics world. There's no way that Shewhart was unaware of what was going on. This is whole development of the Schrodinger equation and the Heisenberg uncertainty principle. And notice there are things here, like the rotary. Matter behaves both like a wave and like a particle. No two electrons can have the same four quantum numbers. You cannot precisely measure location of a particle and its momentum. Okay? The next one is the big. Next slide. Schrodinger wave equation. Okay? Electrons are nothing but waves. They're protons. They have different amplitudes. Are we getting a picture of this? That is how Shewhart is thinking. Okay? He doesn't have a static, random process. He's got a dynamic, deterministic process that under certain conditions looks like it's got random variability. So far, so good? Next slide, please. For Heisenberg, the equation is purely a hypothesis. It's got way too many parameters for the number of possible solutions you can estimate. So as a result, once you have one solution, you have an infinite number of solutions. Classic issue there. But what he was looking at, the Copenhagen interpretation, is these were proper possible outcomes for the measurements. Shewhart's going to twist that a little bit. But then the result is, at this point, quantum mechanics dominates the microscopic universe. The classical laws are dealing at a more macro universe. In modern physics, what we really do is we define reality by what we can measure. And what we measure can then lead to testable hypotheses. Does that sound like statistics? Richard Feynman has a beautiful lecture on YouTube. So look up Feynman's lecture on scientific method. It was a lecture he gave at Cornell just before he won the Nobel Prize in Physics. Noted worldwide for being a great teacher. He's not so popular at NASA because of the Challenger incident, but we won't go there. Okay? He pointed out some follies that they had. But he described scientific method in the following manner. You start with a guess. People started laughing. Feynman was a theoretical physicist. He was guessing. That's a conjecture. Then you calculate the consequences. Well, okay, what would happen if this guess were true? Then you collect data, either through experience or through experimentation, and you compare the data to what you said should happen with your guess. If the data disagree with you, the guess is wrong. End of story. Doesn't matter who you are, doesn't matter how many Nobel Prizes you've won, doesn't matter how beautiful the theory is, it's wrong. Critical role is the data. The data win. I've got that situation with NASA right now, by the way. So sometime this summer you want to talk about it. It's been driving me crazy. But the community has had a whole set of theories, and when we finally did an experiment that would test them, guess what? All of them are wrong. Okay? This is going to be exciting. I'm having fun. Okay? Classic example, my dean was a student of one of the people who got a Nobel Prize for string theory. he said directly, string theory is a religion, no testable hypothesis. Okay? Next slide, please. What's going on in statistics? Key thing here is Neyman Pearson limit is 1933. That's 9 years after 1924. If you want to claim that Shewhart was doing a series of z-tests, you've lost your mind. History refutes that. No way. Because z-test didn't exist then. Z-distribution existed, the z-test didn't. Okay? So, next step. The slides will be available to you. I'm not going to read all of this, but I think it's very important for him to understand that he is trying to explain that which cannot be observed. He's being heavily influenced by the Heisenberg uncertainty principle. Probability is used as a language to describe what we cannot observe. That's the reason why the Schrödinger cat, we don't know if it's alive or dead until we observe it. So, in theory, then it's in two states. No, it's not. It's what's the probability it's in that state? We don't know. It could be either one, but we don't know it until we observe it. And that's going to be fundamental. This is a blinking universe. We have a period of time we can observe it. Okay? Be careful with the term chance, because what he means by chance is because we could not observe it. When we observe it, it's deterministic. But we describe it as chance because we don't know what's going on in between, how it moved from that one state to the other. There's no reference to the central limit theorem, no reference to independence. Where he's concerned about what he calls randomness is that measurement error. It's not with what's going on with the quality characteristics and stuff. So far, so good? Next slide, please. This is his actual equation. He calls X the quality characteristic. I will use Y. I'm a regression guy, and Shewhart did not play with regression, neither did Denny. But what it is, X and a bunch of lambdas, which is the effect of the ith random chance cause. What was the realization? What was that deterministic value? Okay? It was different from the one before. I don't know what caused the change necessarily, but there is a cause underlying it. Okay? But it's deterministic. There's no error term in there. Zero error term. That's not how he's thinking. He's thinking like a physicist. He's not thinking like, he's using probability as language. He's not a probabilist. He's not a statistician. After the observation, X is the current state of the process, given what happened with the lambdas. So far, so good? Okay? And it can happen that a system of chance causes. What he calls a system of chance causes looks like random variation. If it doesn't look like random variation, that would indicate the presence of assignable causes. There are reasons for them. Go find the reasons. Whole idea of control chart. Find the outliers. Fox like to talk about cutting the grass. You start with the tall blades, and then keep moving them down. That's exactly Shewhart's procedure. Next slide, please. I said to think about the blinking universe, and I'll leave this. Y'all can read this. Okay? Next slide, please. There are three conditions for an assignable cause. First, you have to identify it. So you've got to detect it, then you determine what the actual cause is, and then it has to be able to be removed. And that actually is something that many people don't appreciate. Remember, this is the economic control of manufactured product. If it's too expensive to fix the process, given what the benefit would be for fixing it, you don't do it. It's just basic engineering. Am I making sense? If it's something you cannot possibly control, you have to live with it. Get over it. That's basically what he's saying. Okay? So you may have something where you see these blips periodically, but if you couldn't move it, you identified it and couldn't remove it, then you live with it until somebody finds a way to deal with it. Next one, please. Next one. I'll get that. Ultimately, what he's doing is defining upper and lower bounds on the impacts, the effects of the chance causes. His instant decision is economic. He doesn't talk about processed meat at all. No. I'll illustrate that in a control chart in a minute. For him, the observed value of the rational subgroup mean is the mean at that time. We get the picture? And it's deterministic. If you could really observe all of the causes, it would be deterministic. He does rely on randomization theory, but ultimately what he proposes is a manual deadband feedback control loop. That's all he's doing. Next slide. My wife's family is from Lima. I love my sister-in-law's apartment. She complains how cold it is. She has no heat. The windows are always open. She says she wants fresh air. Trust me, there is no fresh air in Lima, Peru. Okay? It's just mind-numbing at one level. She just doesn't want to keep the stale air inside. It's fine. It's fine. I love my sister-in-law. Okay? But she's not alone. There are no heaters or air conditioners. Very rare. I think it's here now. So this is a system under no active control. Got the idea? That does not fly in the United States. So next slide. Blacksburg, Virginia. Heavy investment in heating and cooling. Many, many dollars when you have to replace your heating and cooling unit. It's not pretty. I've had to do it several times in my life. But we want constant, comfortable temperatures. So what do we have? We have a thermostat, and that's an example of an automatic deadband control. In the US, generally the deadband is plus or minus a half degree Fahrenheit, because we set them to rounded numbers in Fahrenheit. You've got the idea? And they can do it. They know how to adjust. It's just, if it's too cold, you add heat. If it's too hot, you add something to cool it. It's not rocket science. Okay? Next slide, please. These are made up data, but this is an example of room temperature in Blacksburg, Virginia. And here is at 71.5. Notice that would be the lower end of a deadband control loop, and that would be the upper band of a deadband control loop to maintain it at 72 degrees Fahrenheit. No rocket science for this. There's no statistics for this. I had to bring online, when I was working for a company, I was a ceramic engineer for 4 years, a brand new furnace for heating pencil lead, of all things, which is a ceramic product. I had to tune the automatic process controller. It was a PID controller. I went to the theory, it was useless, absolutely useless. What did I do? Trial and error until I got something that made good products. At that point, it was a deadband control loop. That's usually the process. But you see, now it looks kind of like a random process, except if you're going out of control here and out of, well, it's out of the band, but what really happened here? Let's go to the next slide. A is when I went to work. So it's in the winter, we turn the heat down. Temperature goes down. Fair enough? I come home from work, I turn the heat back on. It's moving back up. Surprise, surprise. We go to bed, okay? There's less activity going on. Nobody's cooking or anything. It can naturally go down. It's also the cooling effect from outside. D is thermostat starts heating. Got the idea? And it's going to heat it until it hits that band, and then it's going to fall back down. We know the cause for everything in that plot. Welcome to Shewhart. I getting my point across. There's a system of chance causes going on there. Are we at work or are we at home? Is it night? Is it day? Is it a sunny day or a cloudy day? Those are all assignable causes impacting that temperature. Okay? Next slide, please. Shewhart, phase one, what we call now phase one, has a single purpose in his mind: eliminate assignable causes. It's not come up with control limits that seem to work for in the future. It's active investigation, find the outliers, and then correct it. Pages 1921 is a true phase one study. Let me show you the control chart. Next slide, please. This was the initial part of the study. So far, so good? he used what looked like a mean plus three standard deviations, but that was just an arbitrary designation. He just had a line for what is an outlier to the high side, what's a line for what's an outlier to the low side. That's exactly how he's thinking about it. And then he says, okay, go back and see what's common about these things. These probably have a different cause than those. Well, find out. Be an engineer. Discover. It's a discovery process. Here is the control chart afterwards, same time period. This is picking up right at that time period, after they instituted the changes by finding the outliers. Bam. That looks like that's a process in perfect control. However, it's still a very short period of time. It hasn't had a chance to look how the new assignable causes. The assignable causes there, how they're doing under the new system to fully manifest themselves. The Japanese used to do control charts and post them on the wall, showing the evolution of the control limits, exactly like this. You pick up the statistical process control, statistical process monitoring textbooks, you look at those papers, you don't see this. One of the top people in statistical process control thought I was loony when I explained to him what Shewhart was doing. He had no idea that's how Shewhart was analyzing the data. No, because it's not how he analyzes. So far, so good? Next slide, please. So for a simple cause system, you have a finite set of causes. Each has their effects x. So x times the probability of that event creates lambda. We got the idea here? Okay. He assumes constant probability, and he's all assuming they change at the same frequency. Oversimplifications, he admits that. But this thought process of identifying the causes, understanding their effects, and then being able to see where their impact is on the quality characteristic is fundamental to the approach I'm about to show. Okay? Next slide. Justification for approximate normal distribution. He makes a central limit theory-like argument, but it's not by the number of observations, it's for the number of possible causes. I've got a lot of possible causes with my Trent 1000 data. Got the picture? He's thinking of linking universe. I'll leave those alone. Okay, next slide. Assignable cause. Some of the effects are large, and some have much higher probability of occurring. That's all that's going on in Shewhart's world. Those are the assignable causes, so you go and identify them. They allow themselves to be seen. And this is one way to look at his lambdas. It was the effect of the jth cause times the probability jth cause was present. We're going to use something very similar. Next slide. Translation of this. What we have is this is now my quality characteristic. It probably has some kind of mean, and it has some kind of function in terms of the x's. Those x's going back to the specific values of those causes. We can observe those. I've got the engine pump monitoring data. Hello, I got the causes. I got the values. The idea here? That's beginning to look like either a linear or a nonlinear model. Usually it's a nonlinear model. Shewhart didn't want to deal with that. He didn't even want to deal with a linear model. He was just assuming that this would become the noise. This function is the noise. But what you're doing is removing these components over time. There is no error term. Okay? He doesn't think in terms of an error term. It's all deterministic back there. If he could observe everything, he would know it perfect. Okay, next slide. Critical insight. We have a series of profiles. I can superimpose all of them together. That's what I'm going to do. And if you have an in-control process, everything's within proper limits. I'll leave that alone. The economic impact of looking at these characteristics depends upon the specifications on the quality characteristic and not on the individual parameters. Modern statistical process monitoring focuses on changes in the parameters. Well, there's a single quality characteristic. That's where the economic impact is. Why do we care about changes in the parameters if there's no economic impact? That's an interesting question for that group. Next slide. These are real data. I can't tell you anything about it. The Y is simply scaled, okay? The X's have been centered and scaled, so we can't identify their values. I feel comfortable divulging this to you because there's no meaningful information back to the real data. I'm showing concepts. Fair enough? Okay. Now, notice there's a definite trend here. It is a temperature and it's degrading over time. The trend is not surprising. So far, so good? Clearly, it reached a point where it went out of control. That would be an indication something needs to go and we look at what are those causes. Okay, next slide. We went back. Okay, go one more. Let's go forward. Okay, that's the next one. There we go. This is what I want to look at. You get it over. Those are 10 real characteristics of the Trent 1000 jet turbine performance, of that quality characteristic. I have purposely overlaid all 10 for you to get a sense of what it is. Since they're centered in scale, this is actually an individual's control chart. For most of the data, it's sitting there very nicely in control. There are a few points that are outside. But now, this is on the sum of their impacts. This is not on the quality characteristic. This is on the sum of the impacts. This is the components of the noise. I am now separating out the variance components. Here are the variance components all together. Now, how can I find what's really causing the problem? Well, I got your attention. Okay, next slide. Okay, so here's the eye chart of the sum. Next one, please. That's the normal probability plot of the sums. Does that look like a bad normal distribution? It's not random, it's deterministic. But its behavior looks pretty close to being a normal distribution. We had 10 assignable causes. Remember, Shewhart was defining central limit theory not in terms of number of observations, how we normally think, but in terms of the number of causes. We shouldn't be surprised that that sum is beginning to look like a normal distribution. Next slide, please. Here is the individual's chart for X2. Notice it's the image, the degradation in the Y, the increase in the sum was in this direction. So far, so good? Notice X2 is moving in the negative direction of that. That's a clue. That's X2. Next slide. Here's X3, it's even more extreme. So far, so good? The hands are much tighter for the eye chart. Okay? Once again, it's moving in the negative direction. Well, let's look at a regression analysis, where I put all those 10 in there. Next slide, please. There it is. Interestingly, X2 has a very poor p-value, but it is a big driver in the variability of Y. X3 is really doing well, and that's probably because X2 and X3 are at least somewhat collinear with each other. By the way, all 10 of these are significant if you use the press statistic for model selection. I like the press statistic because it's a one-step predicted cross-validation. It's quite robust, like small models. The R-squared, this is looking at just, the R-squared, we're explaining a lot of the variability, just going back and using information about the chance causes. Next slide. Here is the residual plot for the deleted residuals from that regression analysis. We have stripped out the impact of the deterministic variables, and that looks like a really nice control chart. Ultimately, the goal of the Trent 1000 project, we know it's degrading over time. We need to come up with really good predictions of what that temperature is over time. And the tighter that band is, the longer we can run the engine. So far, so good? We've discovered that if we can strip that out, and if we have a problem, we've also discovered where to look first. Hello, this is discovery. This is what statistical engineering is about. This is what Shewhart was talking about. Next slide, please. Shewhart's focus was a simple control loop bit band. He was doing the simplest thing he'd get away with. He wasn't concerned about more complex profiles, and he could never observe what was the actual values of those determinant causes. He was working in the 20s and the 30s. Got the picture? We're now in 2022. We have sensors everywhere. We monitor these things. It leads to data overload because people don't know how to use the data properly to do a journey. Going back to Shewhart's thought, we've got a model to follow. Next slide. The current industrial statistics world really provides little or no insight to that Rolls-Royce problem. Statistical process control, statistical process monitoring is focused on one thing. The experimental design committee, the design world is focused on dealing with optimal designs for small number of factors. Nobody's dealing with these core issues. None of them apply very well directly. If you know how to use them, you can get it there. But the naive use is what is typically done. And the literature thrives off the naive use to the solution because they're coming up with, they have a solution, but they don't understand the problem. And that's what's called a classic error of the third kind, an elegant solution to the wrong problem. You have to understand what the problem is. Okay? Next slide. Rolls-Royce data are a classic example of this. We know as engine performance degrades that PGT is going to increase. There reaches a point then where it is a safety problem and it requires major maintenance. Often requires the replacement of the engine. So what's critical then is accurate predictions of that characteristic. Shewhart's system of causes precisely describes the process and provides a pathway to really, really incorporate massive data efficiently and effectively. And we're illustrating the way. Next slide. Industry 4.0 is real and already here. You got to adapt. It's fun. The more I get to play with it, the more I'm really enjoying. Successful responses require science, engineering, data analysis, business insights. Remember the composition of the overall team for this TRIP 1000 problem. It's right there. Collaboration among the experts is required. Organizational psychology is essential, particularly when you're trying to get the team to work efficiently and effectively together. You don't see all of those skills taught in curriculum. Okay? Very few engineers ever learn anything about organizational psychology. Only the industrial engineers learn anything about project management. All of these are important. Next slide. Proper data analysis requires a basic understanding of the science, engineering, and the business. You don't have to be an expert in it, but you got to be able to understand what the experts tell you, so that then you can do your job in order to create the proper data analysis. The team has to develop instincts about the nature of the opportunity. Instincts like, what is the cause of this problem? And how can I elicit it from the data? Data quality is important, because if we've got bad data, then that is an issue. So data cleansing is an important function, and that's dealing with outliers, but those are outliers for which we know the reason, and we can say why it's an outlier, and we can drop it. Dropping it just because it's a bad value is very dangerous, because it's a missed opportunity to learn. Gotta learn the good, the bad, and ugly of massive data. You know, the good is you have more data on more possible contributors. That's a good thing. We've got a whole lot of variables we haven't fully explored with our data. Too often highly contaminated with incorrect or misleading data. We did not have that problem with the engine health monitoring data. It was very, very clean. I think it had been cleaned before it came to us. Too often, there are so many missing data, you're not able to develop a solution. The ugly, you're looking for a needle in a haystack. The key is how can we extract the necessary information to develop solutions? That's our goal. That's our goal. I think we're almost done. One more slide. Tools are required. Success requires statistical engineering. Statistical engineering means we understand the opportunities full context. We've done our homework on it. We've established what data are necessary. We know what tools to apply and can apply them efficiently, and how to create sustainable solutions. That literally is statistical engineering. And as a final thought, Shewhart's talk from 31 is just as relevant today. In fact, I think more relevant than it was then. So I think the last slide is by one word in Portuguese. Okay? I hope you get a sense of what we're trying to do here. You know, it's wonderful opportunities to deal with very complex problems. Data analysis, data science, machine learning, basic statistics has huge roles to play. But it has to be done in the right context, working with the right people. Everybody's got to drop the arrogance about their professions. You know, it's really fun when you've got a well-working team where you've got expertise and everybody knows how to share it, and you know that the stuff is good. That is a very rewarding experience. And I'm very happy that I'm having that right now. So with that, thank you for the opportunity to speak. I probably went longer than I should have. I apologize. I'm guilty of that often. But again, I'm very excited about working here for the next couple of months. Yeah, Andrew.
How did you come across the original way of thinking of Shewhart, of approaching this problem, since the most usual textbooks is not the way we learn?
Deming said, everybody who says that a control chart is a series of z-tests has no idea what they're talking about. But of course, where did Deming learn how to do a control chart? Directly under Shewhart. They were both working together at Western LA. He was an intern there. There's a classic picture from Western Electric of 5 future honorary members of ASQ, all employees of Western Electric, really good people. So Shewhart always fell in love with the notion of the control chart. Deming fell in love with the idea of the control chart. He stayed good friends with Shewhart the rest of Shewhart's life. Shewhart gave a series of lectures at the United States Department of Agriculture when Deming was there. And that's a book that comes out a little bit later. Deming edited that book. When Deming went to Japan, he was talking to Shewhart hero. So I knew that. And actually, 2 of my friends had tried to read Shewhart and they said it doesn't make any sense to us. So that was a clue to me. I needed to go read it because they were looking at it from their eyes. They weren't trying to look at it from Shewhart's eyes. And once you do that, neither one of them have any engineering training. Neither one of them have any training in science. You know, what they've been doing is pure series of z-tests. This is what we do. This is what the community does. Insulin. The challenge was to go back and read it and really try to understand. It's been fascinating working. We're working with several leading people in statistical process control and monitoring. They haven't quite seen the picture yet. But at least one of them has said frequently, whenever she tries to apply what we publish in the literature to real data, that works. And that's a clue. So that drove me to go look at it. And I really enjoyed doing it. And I've got it all documented. This is going to be a series of papers I do over the next few years. But it will be a challenge to that community, but I'm trying to challenge it in a correct way. But I think the best way to do it is to illustrate it through success stories. I think we're building one right now. Thank you. Fair enough? Yes, please.
Eu gostaria, Felipe, que você venha aqui bastante no microfone, porque senão o pessoal do YouTube não escuta. O pessoal está querendo escutar. Se você esteja escutando.
Oh, the microphone.
Professor Vining, I'm also a professor here. I'd like to know who should we blame, or maybe in some cases, for you Schubert's idea for statistical process control as a series of random events, as opposed as deterministic ones.
What it is when you look at, I'll go back to my own training. And I was trained by a very good person in statistical process. And was trained immediately as this is a series of z-tests. And if you look at it at the end of the process, this is what Shewhart was talking about, then it really does look like that. But the problem is, how do you get to that end point? So all the publications in like the 40s and the 50s, even into the 60s, tended just to do what they call the control chart. And they just assumed that you had gotten in a state of control, and then here were the occasions where it was out of control. No one had talked about the journey. It was the series of z-tests, because that's how they understood it. Very natural, right? I looked at it that way. So I'm just as guilty as the rest. When I was the editor of the Journal of Quality Technology from, what was it, 96 to 99, I published a lot of these papers, and they all look fine to me. It's only as I get older and get to deal with more real problems that I begin to see there's real limitation in this. And that's the reason why I wanted to go back to the original Shewhart, because I had heard Deming say, these people don't understand Shewhart at all. And it turns out Deming was correct. So it was an odyssey for me, a journey for me to go and discover what did Shewhart really say. And I had a PhD student working at that time. We were dealing with nonlinear modeling of the growth of shrimp in Peru. And we built a control chart for that. But it was using the full nonlinear model. Very different from the current literature. She's had trouble getting papers published. She's having success, because it's a very different way of thinking about the problem than the statistical process monitoring is. This was going on at the same time as I was studying Shewhart. In fact, she studied Shewhart in that process. It's just, we take things for granted. We take the easy way out. And all of us are guilty of that. So this is not to press blame, but rather it's important for us to shine the light when this happens, not in an antagonistic way, but illustrate, here are problems where what we claim just can't work. And that's what I'm hoping to do with this thing. The goal of this Trent 1000 is to build digital twins, true digital twins, so that you can manipulate that, do experimental designs on that, and not worry about it blowing up. Digital twins are very powerful tools, but you have to understand the real process. When I was first doing this, I actually built a digital twin of the pencil lead process I worked on from 1981 to 1985. I had real data from 1985. And I could mimic it quite well by memory, by going back to the deterministic relationships, all of the nonlinear functions. They were talking about the removal of water, or the strengthening of pencil lead from the furnace. It was a fascinating experience to be able to say, oh, I can mimic this. In the automatic process control literature, there is the Tennessee Eastman process, which was Fortran code written in the early 90s. And they did that to, as a competition, can you come up with an optimal automatic process control algorithm? There they weren't dealing with a quality characteristic, they were dealing with like, I want this to be this pressure, how can I keep it at that pressure? What kind of disturbances happen that will take it off in the wrong direction? Similar, but not exactly the same problem. So friends of mine in Scandinavia, primarily Sweden, but also Denmark, have been using the Tennessee Eastman process to evaluate experimental designs of continuous processes. But there, the Tennessee Eastman process doesn't work well for that. It just doesn't. It gives you nonsense. So and this is the same time I wanted a real digital twin to illustrate these concepts when that was accepted. So now I've got a master's level statistics student tweaking, going back into the Tennessee Eastman code so that we can do it for experimental design purposes and make it more available as a digital twin to evaluate these kind of questions. The problem in too many communities today is proof by simulation. That's not a proof. If you assume a bunch of stuff, and then you create the optimal test statistic for that bunch of stuff, surprise, surprise, if the data follow exactly what you claim, it's wonderful. The test is how was it explained? Real data. That was the comment that I was getting from my friend when we were doing this Shewhart study. Has it really changed your research? A little bit. Does it frustrate her that some of her papers don't get published? Yes. Is she an editor of a major journal now? Yes. But she's not changing that community. She's aware of the issues, which I think is hopeful. But again, we have too many fields. Experimental design does this, time series does this, reliability does this. It's proof by simulation. How does it deal with real data? So that's why having digital twins would be a huge advance for what we do, because that's becoming more realistic. But what's even better is when you have the opportunity to work on a project like I'm working. I've had a Rolls-Royce project, I've had a NASA project. This NASA project is not reliability, beyond belief. Bill Meeker is the expert on reliability. No comparison. But he doesn't understand experimental design. He doesn't understand your
I went twice, State.
Yeah. Bill's a great person. Bill wrote one of my letters of recommendation for the full law. He said, I have the greatest respect. He's got the greatest respect for me. He said, I know reliability a lot better than he knows regression model. Okay? So as a result, there are certain areas where I'm going to have a real advantage. The NASA project is. Does that make sense? But that's where collaboration is important. It's where learning other fields, where curiosity is critical. And that's what we got to do.
I don't have questions, but I'd like to be part of this team.
Okay.
Yeah, but
Excellent.
I don't have questions. I see your so excitement.
We want to train students in this kind of process. Yeah?
So different of what you study, different.
Yeah, but when you're in a good organization, what's the first thing they're going to teach you? I'm hopeful it's a good one who knows how to handle it and take full advantage of it. They're going to teach you these skills. Problem is, not many organizations have understood that this is the process we need to do. Hence the need to form this discipline of statistical engineering. And that's one of the steps. So for all the students in the course, a course requirement is to join the International Statistical Engineering Association. By the way, it's free. Okay? And that's because the textbook is only available to members of the International Statistical Engineering Association. But it's free. Okay? Don't get mad at me. It's free. Okay? You don't have to buy a textbook. You just download it. Okay? So I think it's fair.
I have a message from Linda.
Okay. Oh, Linda, go ahead.
Yes, she's watching you.
Excellent.
She says, "Hi, Geoff. Here it's Linda. It's a pleasure to see and hear you. I missed your message. So far, so good."
Oh, that's great. Linda, I hope to be able to see you sometime this summer. We need to arrange a trip to San Paulo so I can come and visit and talk.
So no more questions. So I think that's it. Thank you so much.
Thank you.
Muito obrigada a todos. Obrigado a todos pela presença e obrigado também aos que nos assistem, nos acompanham pelo YouTube.
Bye.
Eu acho que a gente tem um pouco de